Spanning across approximately 93 billion light-years in diameter, the observable universe is a vast cosmic bubble containing all that can be seen or detected from Earth. This includes every star, planet, galaxy, and speck of cosmic dust that light has had enough time to reach us since the universe's birth about 13.8 billion years ago. Despite its seemingly incomprehensible size, it represents just a fraction of the entire universe, which stretches far beyond what we can observe. What mysteries lie beyond the universe? Scientists use the speed of light as a measuring stick for the universe's age and size. Since light travels at a fixed speed of about 300,000 kilometers per second, we can only see as far as light has had the chance to travel since the universe's inception. This concept nurtures not only our understanding of the cosmos, but also our curiosity about what lies beyond the cosmic horizon in the unobservable universe. The unobservable universe, stretching far beyond the limits of our current detection capabilities, emerges as a realm that defies comprehension. While the observable universe extends for about 93 billion light-years in all directions, the unobservable universe is believed to be exponentially larger, possibly infinite. Current theories suggest that our observable universe is merely a tiny bubble within an incomprehensibly vast expanse. If the inflation theory holds true, which posits that the universe expanded at a rate far exceeding the speed of light just moments after the Big Bang, then what lies beyond could be boundless, teeming with countless other observable universes like our own, each with its own galaxies, stars, and planets. The exact size of this unobservable space is beyond the grasp of current scientific knowledge, leaving us to marvel at the mystery and infinite potential of the cosmos. At the heart of the cosmos, the universe's composition is elegantly simple yet profoundly complex, consisting of three primary components: matter, dark matter, and dark energy. Matter, which makes up about 5% of the universe, includes the atoms and particles that form stars, planets, galaxies, and everything visible to us. Embarking further into the cosmic unknown, dark matter, accounting for about 27% of the universe, remains invisible and detectable only through its gravitational effects on visible matter. Dark matter acts as a cosmic scaffolding, guiding the structure and formation of galaxies. The most dominant yet elusive component is dark energy, making up approximately 68% of the universe. This mysterious force is driving the accelerated expansion of the universe, acting against the gravitational pull of matter. Together, these components weave the fabric of the cosmos, from the smallest particles to the largest galactic structures, encapsulating the beauty and mystery of the universe. Astronomers have devised ingenious methods to measure cosmic scales. The initial step into this vast measurement uses the familiar unit of light years, the distance light travels in 1 year, roughly 9 trillion kilometers. For nearer cosmic objects, such as planets or stars within our galaxy, the method of parallax comes into play, where the apparent shift in an object's position, when observed from two different points in Earth's orbit, is used to calculate its distance. As we reach further into space, measuring distances becomes more challenging and relies on standard candles like Cepheid variable stars, whose intrinsic brightness is well understood, allowing astronomers to deduce their distance based on how bright they appear from Earth. For the most remote objects, such as distant galaxies, the redshift method is employed, where the stretching of light to longer, redder wavelengths due to the expansion of the universe provides clues to their distance and speed. Through these methods, astronomers piece together the cosmic puzzle, bridging the vast distances of space with the precision of scientific inquiry. Dark energy, a mysterious force that permeates all of space, has been one of the most profound discoveries in cosmology. It accounts for about 68% of the universe's total energy and acts as the driving force behind the accelerated expansion of the universe. Unlike gravity, which pulls objects together, dark energy pushes them apart, working against the gravitational attraction of matter. Its effects were first observed in the late 1990s through studies of distant supernovae, which showed that galaxies are moving away from each other at an increasing rate. The nature of dark energy remains one of the greatest mysteries in science. It doesn't emit or absorb light, making it incredibly difficult to detect directly. Its presence is inferred from its gravitational effects on the cosmos's structure and expansion. Understanding dark energy is not just a quest to comprehend the universe's present state, but also to predict its ultimate fate. Will the universe expand forever, or will dark energy change over time, leading to a different cosmic end? The quest to unravel the nature of dark energy continues to challenge and inspire scientists around the world. Dark matter, an invisible yet profoundly influential component of the universe, plays a crucial role in its structure and evolution. Constituting about 27% of the universe's mass energy content, dark matter does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects. Its presence is essential for explaining the observed behaviors of galaxies and galaxy clusters that cannot be accounted for by the gravitational pull of visible matter alone. Dark matter acts as a cosmic glue, holding galaxies together and preventing them from flying apart as they rotate. It also serves as a framework for the large-scale structure of the universe, with galaxies and galaxy clusters forming along the densest regions of dark matter. Without dark matter, the gravitational forces generated by visible matter alone would be insufficient to form the galaxies and other large structures that we see in the universe today. By influencing the distribution and movement of galaxies across the cosmos, dark matter plays a foundational role in shaping the universe's vast and intricate web. Galaxies, the majestic structures hosting stars, planets, gas, and dust, are born from the primordial fluctuations in the density of the universe's matter shortly after the Big Bang. These minor perturbations serve as seeds for the gravitational pull, gradually attracting nearby matter and dark matter over millions of years. The process kicks off with gas clouds cooling and collapsing under gravity, leading to the birth of the first stars. These early stars and subsequent generations inject energy and heavier elements into their surroundings, fostering the formation of more stars and the eventual emergence of a galaxy. As time marches on, galaxies evolve through various processes. They can grow by accreting gas from the intergalactic medium and converting it into new stars. Significant growth spurts occur through mergers and interactions with other galaxies, which can dramatically alter their shapes and star formation rates. Over billions of years, spiral galaxies might transform into elliptical galaxies due to these violent encounters. Meanwhile, isolated galaxies might continue forming stars at a steady pace or exhaust their gas, turning into dormant realms filled with older stars. The life cycle and evolution of galaxies are testament to the dynamic and ever-changing nature of the universe, shaped by gravity, the interstellar medium, and the intricate dance between galaxies. The cosmic microwave background, CMB radiation, stands as one of the most significant discoveries in cosmology, offering a window into the universe's infancy. This faint glow, permeating the entirety of space, is the afterglow of the Big Bang, the momentous event that gave birth to the universe approximately 13.8 billion years ago. The CMB was first detected accidentally in 1965, but its significance was quickly realized. It provided the most compelling evidence for the Big Bang theory. This relic radiation, now cooled to just 2.7 degrees above absolute zero, bears the imprints of the young universe, about 380,000 years after its genesis, when particles and light finally decoupled, allowing light to travel freely. The minute fluctuations in the CMB's temperature reveal the initial distribution of matter, serving as the seeds for the formation of galaxies and the large-scale structure of the universe. Moreover, the CMB has shaped our understanding of the universe's composition, age, and rate of expansion. Through detailed observations of the CMB by satellites such as COBE, WMAP, and Planck, cosmologists have refined the standard model of cosmology. The CMB not only underscores the universe's dynamic evolution from a hot, dense state, but also continues to guide our inquiries into the cosmos's deepest mysteries, such as the nature of dark matter and dark energy. The ultimate fate of the universe is a captivating subject that has intrigued scientists and stargazers alike, with three prevailing theories painting starkly different cosmic endgames: the Big Freeze, the Big Rip, and the Big Crunch. The Big Freeze scenario, considered the most likely based on current understanding, suggests the universe will continue expanding at an accelerated pace, driven by dark energy. Over trillions of years, galaxies will drift apart, stars will burn out, and black holes will evaporate. The universe will become a cold, dark, and desolate expanse, with temperatures gradually approaching absolute zero. In contrast, the Big Rip theory posits that dark energy's force could become so dominant that it will not only drive galaxies apart, but will also tear apart stars, planets, and eventually even atoms themselves, ripping the very fabric of space-time. The Big Crunch envisions a gravitationally dominated cosmos, where the expansion eventually halts and reverses into a contraction, culminating in all matter and space-time being pulled back into a singular, infinitely dense point, potentially setting the stage for another Big Bang. Each of these theories rests on deep underlying questions about the nature of dark energy, dark matter, and the fundamental laws governing the cosmos. As our understanding evolves, so too will our insights into the ultimate destiny of the universe. The concept of a multiverse, where our universe is just one of potentially countless others within a grander cosmic expanse, has moved from science fiction to a serious theoretical consideration in physics. Among the leading theories about the multiverse, a few stand out due to their implications and the scientific frameworks that support them. Firstly, there's the quantum multiverse, stemming from the interpretations of quantum mechanics, particularly the many worlds interpretation. It suggests that with every quantum decision or event, the universe splits, creating an immense, perhaps infinite number of parallel universes that diverge from each other based on the different outcomes of these events. Another compelling idea is the cosmic inflationary multiverse, which extends from the theory of cosmic inflation. It proposes that during the early universe's rapid expansion, different regions might have stopped inflating at different times, leading to bubble-like pocket universes within a much larger space. Each of these pockets could have different physical laws and constants. Multiverse comes from the mathematics of string theory, which might allow for numerous ways the extra dimensions it posits are configured. Each configuration would lead to a different set of physical laws, suggesting a landscape of various universes with diverse properties. Finally, the parallel brains concept within string theory and M-theory postulates that our three-dimensional universe exists on a brain, a multi-dimensional object, within a higher dimensional space. Other brains floating in this higher dimensional space could host their own universes, with potentially close but non-intersecting worlds. These theories, while still speculative without direct evidence, open vast avenues for understanding our place in the cosmos, suggesting that our universe could be just one of an unimaginable number of universes in a much larger multiverse. The title of the largest known galaxy, as of current astronomical findings, belongs to IC 1101. Situated at the heart of the Abell 2029 galaxy cluster, approximately 1 billion light-years away from Earth, IC 1101 is a supergiant elliptical galaxy that stretches over 4 million light-years in diameter. To put its immense size into perspective, the Milky Way is about 100,000 light-years across, making IC 1101 nearly 40 times larger. Discovered by British astronomer Frederick William Herschel in 1790, this colossal galaxy is thought to have formed through the merger of many smaller galaxies over billions of years. Its vast size hosts potentially trillions of stars, far more than the estimated 200 to 400 billion stars in our own galaxy. IC 1101's enormity provides a fascinating glimpse into the scale of cosmic structures and the processes that can lead to such mammoth formations in the universe. Supermassive black holes, lurking at the centers of most, if not all, large galaxies, play a pivotal role in the formation and evolution of galaxies. These cosmic behemoths, which can be millions to billions of times the mass of the Sun, wield a significant influence over their host galaxies despite their relatively small size compared to the galaxy as a whole. One way supermassive black holes influence galaxy formation is through the regulation of star formation. As material spirals into a black hole, it heats up and emits intense radiation and jets of particles at nearly the speed of light, in phenomena known as quasars or active galactic nuclei. This radiation and particle jets can heat surrounding gas or blow it out of the galaxy's central regions entirely, preventing the gas from cooling and collapsing to form new stars. This self-regulatory mechanism is thought to explain why the universe has fewer large, bright galaxies than would be expected if star formation proceeded unchecked. The relationship between the mass of a supermassive black hole and the properties of its host galaxy's bulge, such as the bulge's mass and the speed of stars within it, suggests a deep connection between black holes and galaxy formation. The precise nature of this connection remains an active area of research, but it likely involves complex feedback processes where the growth of black holes and the formation of galaxies influence each other. The Great Attractor is a gravitational anomaly located roughly 250 million light-years from the Milky Way in a region of space known as the Norma Cluster. This mysterious area exhibits a gravitational pull so immense that it affects the motion of galaxies over hundreds of millions of light-years away, including our own Milky Way galaxy. Despite being obscured by the plane of our galaxy, making direct observations challenging, the Great Attractor's influence is detected through the peculiar velocities of galaxies, their motion relative to the cosmic expansion. What makes the Great Attractor particularly fascinating is its role in revealing the large-scale structure of the universe. Galaxies, including the Milky Way and its neighbors, are not just moving away from each other due to the universe's expansion, they're also being pulled towards regions of higher gravitational attraction, like the Great Attractor. This massive structure is thought to lie at the heart of the Laniakea supercluster, a colossal collection of galaxies and galaxy clusters that includes our own. The Great Attractor's impact extends beyond just altering the trajectories of local galaxies. It provides key insights into the distribution of matter, both visible and dark, in the universe. This, in turn, helps astrophysicists understand the universe's overall structure and the dynamics governing it, shedding light on forces that sculpt the cosmos on its grandest scales. Galaxies can collide, and these cosmic encounters are far more common than one might initially think. When galaxies draw near, their mutual gravitational attractions can set them on a collision course, leading to a dramatic merge that can take hundreds of millions of years to complete. Despite the vast number of stars within them, direct star collisions are rare due to the immense distances between stars. Instead, the gravitational forces dramatically warp and reshape the galaxy's structures. During a galactic collision, gas clouds can smash into each other, creating shock waves that compress the gas and trigger new waves of star formation, lighting up the galaxies with the birth of new stars. These periods of intense star formation are known as starbursts. The collision can also feed the supermassive black holes at the galaxy's centers, leading to active galactic nuclei or quasars that emit vast amounts of energy. Over time, the two galaxies will merge their stars, gas, and dark matter into a single, larger galaxy. The resulting shape may be different from the original galaxies, often resulting in an elliptical galaxy, even if the progenitors were spiral galaxies. One of the most famous examples of colliding galaxies is the ongoing interaction between the Andromeda Galaxy, M31, and the Milky Way, which are expected to collide in about 4 billion years. This cosmic event will likely transform both galaxies, merging them into a new, larger entity, sometimes referred to as Milkomeda in popular science discussions. Through these colossal encounters, galaxies evolve, change shape, and sometimes even form entirely new types of galaxies, showcasing the dynamic and ever-changing nature of the universe. Quasars, or quasi-stellar objects, are among the most luminous, powerful, and energetic objects in the universe. Nestled in the centers of galaxies, they are powered by supermassive black holes. As matter spirals into these black holes, it heats up and emits enormous amounts of light and other radiation, making quasars visible even at the very edges of the observable universe. The importance of quasars cannot be overstated. They serve as cosmic lighthouses, illuminating the dark epochs of the early universe, and provide crucial insights into the formation and evolution of galaxies. By studying quasars, scientists can probe the conditions of the universe when it was only a fraction of its current age, offering a window into the past and helping to unravel the mysteries of the cosmos. The Bootes void, discovered in 1981, is a vast expanse of space that is strikingly empty. Spanning over 300 million light-years in diameter, it is one of the largest known voids in the universe. This region contains far fewer galaxies than expected, making it a cosmic desert in the vastness of space. The reason for its emptiness remains a topic of debate among astronomers. Some theories suggest that it may be a result of the way large-scale structures in the universe formed, with matter clustering along filaments and leaving behind vast empty regions. Others propose that the void could have been cleared out by the expansive forces of the universe's inflationary period. Despite its emptiness, the Bootes void offers valuable insights into the large-scale structure of the cosmos and the processes that shaped it, inviting further exploration into the mysteries of the universe. Galaxy filaments are the largest known coherent structures in the cosmos, forming a gigantic web-like arrangement that spans the universe. These immense strands of galaxies and dark matter stretch across hundreds of millions of light-years, surrounding vast voids and creating a cosmic web that underpins the structure of the universe. Filaments are not just random arrangements. They are a direct consequence of the uneven distribution of matter following the Big Bang, shaped further by the gravitational pull of dark matter. Understanding galaxy filaments is crucial for astronomers as they reveal the universe's large-scale structure and offer insights into the distribution of dark matter, the evolution of galaxies, and the dynamics of cosmic expansion. By studying these majestic cosmic threads, scientists can piece together the history and the underlying mechanics of the universe, providing answers to some of the most fundamental questions in cosmology. There are galaxies that roam the cosmos without belonging to a traditional galaxy cluster. These isolated wanderers, often referred to as rogue galaxies or intergalactic wanderers, lead a solitary existence, drifting through the vast emptiness of space, far from the gravitational embrace of a galaxy cluster or group. Rogue galaxies can become detached from their native groups due to gravitational interactions, which can fling them out into the vast cosmic sea, or they may have formed in isolation. Studying these rogue galaxies is crucial for astronomers, as they offer unique insights into galaxy formation and evolution outside the complex dynamics of crowded environments. Their isolated nature allows scientists to observe the properties of galaxies without the interference of nearby cosmic objects. Despite their solitary paths, these rogue galaxies remind us of the diversity and vastness of the universe, continually challenging our understanding of cosmic structures and dynamics. Scientists study the gas and dust between galaxies, known as the intergalactic medium, IGM, using a variety of advanced astronomical techniques. One primary method involves observing the light from distant quasars, which serves as a backlight illuminating the IGM. As the light from a quasar travels through the universe, it interacts with the gas and dust scattered between galaxies. This interaction leaves specific signatures in the light spectrum, known as absorption lines, each corresponding to different elements and their states in the IGM. By analyzing these absorption lines, scientists can decipher the composition, density, temperature, and even the motion of the material in the IGM. Another method includes using radio telescopes to detect the faint glow of neutral hydrogen gas, which can reveal the density and structure of the IGM in great detail. These studies are crucial for understanding the life cycle of galaxies, as the IGM acts as both a reservoir feeding galaxies with material and a repository for the material expelled from galaxies, ultimately shaping the evolution of the cosmos. A starburst galaxy is a type of galaxy undergoing an exceptionally high rate of star formation, compared to the more sedate pace observed in typical galaxies like our own Milky Way. In these cosmic cauldrons, stars can form at a rate tens or even hundreds of times faster, lighting up the galaxy with new stellar life. This frenetic activity is often triggered by gravitational interactions or collisions with other galaxies, which compress the gas and dust, creating the perfect conditions for stars to form en masse. Starburst galaxies are not only spectacular to observe, but also serve as critical laboratories for understanding stellar formation and evolution. The intense bursts of star formation are relatively brief on cosmic timescales, lasting only a few tens of millions of years, but they can have profound effects on the galaxy's future, exhausting vast amounts of gas, seeding the interstellar medium with heavy elements produced by supernova, and influencing the formation of subsequent generations of stars. Among the vast array of stars in the universe, several types stand out due to their unique and extraordinary characteristics. Magnetars, a type of neutron star, are one such example, possessing the most intense magnetic fields known in the universe, trillions of times stronger than Earth's. This immense magnetic power can fuel spectacular outbursts of gamma rays and X-rays. Another unusual type is the Thorne-Zitkow object, TZO, a theoretical and extremely rare star hypothesized to form when a neutron star is engulfed by a giant or supergiant star, creating a bizarre hybrid that challenges our understanding of stellar evolution. Additionally, there are Wolf-Rayet stars, massive stars in a brief, violent phase of their life cycle, characterized by incredibly strong winds that blow off their outer layers, exposing the hot, bright core. Their rarity and the stunningly beautiful nebulae they produce make Wolf-Rayet stars one of the cosmos's most extraordinary phenomena. Lastly, pulsars, which are highly magnetized, rotating neutron stars that emit beams of electromagnetic radiation, are also remarkably unusual. The precision of their observed pulses, often likened to cosmic lighthouses, has profound implications for the study of fundamental physics, including tests of general relativity. These stars, among others, underscore the universe's diversity, offering fascinating windows into the extreme conditions and processes that govern stellar life and death. A star becomes a supernova through one of two principal processes, both leading to a spectacular and violent explosion that marks the end of the star's life cycle. The first process involves a massive star, at least 8 times the mass of our Sun. In the final stages of its life, the star exhausts its nuclear fuel, leading to a failure in generating the necessary outward pressure to counteract its own gravitational pull. Consequently, the core collapses under gravity in a fraction of a second, causing the outer layers of the star to explode in a core collapse supernova. The second process occurs in a binary star system where one of the stars is a white dwarf. The white dwarf accumulates matter from its companion star, gradually increasing in mass until it approaches a critical limit, known as the Chandrasekhar limit, approximately 1.4 times the mass of the Sun. Beyond this point, the star can no longer support the extra weight, leading to a runaway nuclear fusion reaction that ultimately results in a thermonuclear supernova. Both types of supernovae play crucial roles in the cosmos, dispersing heavy elements necessary for life into the interstellar medium and influencing the formation and evolution of subsequent generations of stars and planetary systems. A magnetar is a type of neutron star, distinguished by its extraordinarily strong magnetic field, which is up to 1,000 times stronger than that of a typical neutron star. Neutron stars, the dense remnants of supernova explosions, are already known for their extreme conditions, including incredibly fast rotation speeds and strong magnetic fields. However, magnetars take these extremes to another level, possessing magnetic fields that can exceed 10 trillion Gauss. Earth's magnetic field, for comparison, is about half a Gauss. This intense magnetic field of a magnetar is capable of powering spectacular astronomical events, including bursts and flares of X-rays and gamma rays, making them some of the most magnetic objects in the universe. The immense energy released by these magnetic fields can distort the magnetar's shape, leading to starquakes that further enhance the emission of high-energy radiation. While the exact mechanism behind the formation of such strong magnetic fields remains a topic of ongoing research, it is believed that it could be related to the rapid spin and the resulting dynamo effect during the early stages of the neutron star's evolution. The unique properties of magnetars not only differentiate them from regular neutron stars, but also make them objects of intense study, as they provide insights into the behavior of matter and magnetic fields under the most extreme conditions found in the universe. Are stars always hot? No, actually, a star can be colder than the human body. These stars, known as brown dwarfs, are often referred to as failed stars because they do not have enough mass to initiate hydrogen fusion in their cores, which is the process that powers true stars like our Sun. Without this fusion, brown dwarfs do not emit much light but do release heat. The temperatures of brown dwarfs can range from as hot as a few thousand degrees Celsius to as cool as room temperature, and in some cases, even colder. The coolest brown dwarfs discovered so far have temperatures that can dip below the average human body temperature of 37 degrees Celsius, 98.6 degrees Fahrenheit. These exceptionally cool objects challenge the traditional boundaries between stars and planets, exhibiting properties of both, and provide valuable insights into star formation and the diversity of objects in the universe. Hypernovae are exceptionally energetic and luminous stellar explosions that far outshine typical supernovae. They release a staggering amount of energy, sometimes equal to the output of a typical supernova, but compressed into a much shorter time frame, and are thought to be the result of the collapse of very massive stars, possibly leading to the formation of black holes. What sets hypernovae apart from other explosive stellar events is not just their incredible luminosity, but also their association with long-duration gamma-ray bursts, GRBs, which are intense jets of gamma radiation shot into space at nearly the speed of light. These bursts can last anywhere from a few seconds to several minutes, and they are among the most powerful phenomena in the universe, detectable across vast cosmic distances. The exact mechanism behind hypernovae and their connection to GRBs is an area of active research, but it is believed that the rapid rotation and powerful magnetic fields of these stars play a crucial role in focusing and propelling the jets of energy that characterize these events. By studying hypernovae and their aftermath, astronomers hope to gain insights into the life cycles of massive stars, the conditions required for the formation of black holes, and the processes that drive the universe's most energetic explosions. A pulsar is a highly magnetized, rotating neutron star that emits beams of electromagnetic radiation out of its magnetic poles. This radiation can include radio waves, X-rays, and gamma rays, depending on the pulsar. Because the magnetic poles and the rotation axis are misaligned, the radiation beams sweep across the sky, and when one of these beams crosses Earth, it can be detected as a pulse. This gives pulsars their name, derived from the appearance of pulsating signals they produce. Pulsars rotate with incredible regularity, and some can be as precise as atomic clocks, making them invaluable astronomical tools. Pulsars offer a window into the extreme conditions of the universe that can't be replicated on Earth. They help scientists study the behavior of matter under intense gravity and magnetic fields, test theories of relativity, probe the interstellar medium, and even detect gravitational waves through precise timing of pulsar signals. The extreme precision of pulsar timings is also used in attempts to develop a galactic-scale navigation system. Each pulsar has a unique timing and electromagnetic signature, making them cosmic lighthouses that offer a beacon for understanding the universe's vast and dynamic nature. Binary star systems consist of two stars that are gravitationally bound to each other and orbit a common center of mass. These systems range from close binaries where the stars are so near that they can exchange mass or even merge, to wide binaries where the stars are so far apart that their interactions are minimal. The significance of binary star systems in astronomy cannot be overstated, as they provide critical insights into stellar dynamics, formation, and evolution. Studying binary stars allows astronomers to measure stellar masses and radii with high accuracy, which are crucial for testing theories of stellar structure and evolution. Observations of mass transfer in close binary systems help to understand the life cycle of stars, including the formation of exotic objects such as neutron stars and black holes. Furthermore, binary star systems are key to understanding the processes behind supernova and the synthesis of heavy elements in the universe. Some binary systems, especially those containing pulsars or eclipsing binaries, also serve as natural laboratories for testing the fundamentals of physics, including the effects of gravity in strong field regimes. Overall, binary star systems are foundational to our understanding of the cosmos, providing a wealth of information about the life and behavior of stars. The life cycle of a star is a fascinating journey that spans millions to billions of years, depending on the star's mass. It begins in a cold, dense cloud of gas and dust known as a molecular cloud. Under the force of gravity, parts of this cloud begin to collapse and form a protostar. As the protostar accumulates more mass, its temperature and pressure increase until nuclear fusion ignites in its core, marking the birth of a true star. In the main sequence phase, the star achieves a stable equilibrium, fusing hydrogen into helium in its core. This phase, where the star spends the majority of its life, is characterized by a balance between the gravitational forces pulling the star inward and the outward pressure from nuclear fusion. For a star like our Sun, the main sequence phase lasts about 10 billion years. As the star exhausts its hydrogen fuel, it leaves the main sequence. For stars like the Sun, they expand into red giants, fusing helium into carbon and sometimes oxygen in their cores. The most massive stars can fuse elements all the way up to iron. Eventually, the star sheds its outer layers, leaving behind a dense core. For stars up to about 8 times the mass of the Sun, this remnant is a white dwarf. For more massive stars, the core's collapse leads to a supernova explosion, leaving behind either a neutron star or, for the most massive stars, a black hole. Throughout their lives, stars are not only engines of nuclear fusion, but also cosmic forges, creating the heavier elements that make up much of the universe, including the components essential for life. The life cycle of a star is a key process in the evolution of the cosmos, influencing the formation of subsequent generations of stars and planetary systems. As of now, dark stars remain a theoretical concept and have not been directly observed. The idea behind dark stars suggests that they could be early stars in the universe powered not by nuclear fusion, as in conventional stars, but by the annihilation of dark matter within them. Because dark matter does not interact with electromagnetic radiation in the same way as normal matter, dark stars would not emit light in the usual wavelengths, making them incredibly challenging to detect with current observational technologies. Scientists speculate that if dark stars exist, they would be detectable through indirect methods, leveraging the influence they would have on their surroundings and the unique signatures they might leave behind. For instance, dark stars could alter the patterns of cosmic microwave background radiation or influence the formation of structures in the early universe in observable ways. Additionally, certain types of dark matter annihilation could produce unique gamma-ray signals detectable with current or future gamma-ray observatories. The study of dark stars, therefore, involves a combination of theoretical physics, computer simulations, and indirect observational strategies, aiming to understand how these hypothetical objects would form, evolve, and impact their cosmic environments. Discovering dark stars would provide unprecedented insights into the nature of dark matter, the conditions of the early universe, and the diversity of stellar objects. Among the celestial cast, the most massive stars we know play a pivotal role in the cosmic drama. These astronomical giants, often over 100 times the mass of our Sun, are not just remarkable for their sheer size, but for their life cycle and influence on the cosmos. Born from the densest clouds of gas and dust, their lives, although short-lived in the astronomical sense, spanning millions instead of billions of years, are intensely radiant and energetic. As they reach the end of their lifespans, their deaths are nothing short of spectacular, giving birth to some of the universe's most stunning phenomena such as supernovae, neutron stars, or even black holes. But their significance extends beyond their dramatic finale. Throughout their existence, they are alchemists at the heart of cosmic evolution, forging every element heavier than hydrogen and helium. Through their explosive demise, they scatter these elements across the galaxy, seeding the clouds that will give rise to new stars, planets, and potentially life itself. Thus, the most massive stars we know are not just awe-inspiring due to their size and power, but are also key players in the narrative of the universe, contributing to the complex process that makes the existence of everything from galaxies to living organisms possible. An exoplanet, a term that stands for extrasolar planet, refers to a planet that orbits a star outside our solar system. These celestial bodies, hidden vast distances away from us, have captured the imagination and keen interest of scientists and astronomy enthusiasts alike. Their discovery marks one of the most thrilling advancements in modern astronomy, offering a fresh perspective on the potential for life beyond our solar system. Unlike the planets within our own celestial neighborhood, exoplanets present a diverse array of sizes, compositions, and environments, with some nestled in the habitable zones of their stars, where conditions might be right for liquid water and potentially life to exist. Owing to the ingenuity and advancement in technology such as the Kepler telescope, thousands of these distant worlds have been identified since the first confirmed discovery in the 1990s. Each discovery adds a new piece to the cosmic puzzle, expanding our understanding of the universe's complexity and the widespread potential for planets like our own. The study of exoplanets not only challenges our notions of planetary formation and system architecture, but also holds the promissory note of answering the age-old question, are we alone in the universe? Astronomers detect exoplanets through a variety of ingenious methods, each revealing different facets of these distant worlds. One of the most commonly used techniques is the transit method, which observes the dimming of a star's light as an exoplanet passes in front of it. This minuscule dip in brightness allows astronomers to infer the planet's size and its orbit. Another fascinating technique is the radial velocity method, often referred to as the wobble method. Here, scientists detect slight movements of a star towards or away from us, caused by the gravitational pull of an orbiting planet. This method can provide information about the planet's mass and the shape of its orbit. Direct imaging involves capturing visual images or spectra of exoplanets by blocking out the overwhelming light of their host star, an approach that is akin to taking a photograph. Although challenging and currently possible for only a few exoplanets, this method holds the potential to study the planet's atmosphere and chemical composition. Lastly, the gravitational microlensing method relies on the gravitational field of a star with an orbiting planet bending the light of a more distant background star. This temporary increase in brightness can reveal the presence of an exoplanet. Each of these methods has its strengths and weaknesses, but together they form a powerful toolkit for astronomers, enabling the discovery and study of a vast and varied array of exoplanets across the galaxy. As of recent discoveries, the title of the most Earth-like exoplanet often shifts as new worlds are uncovered and our understanding of habitability deepens. However, one notable contender is Kepler 452b. This exoplanet, discovered by the Kepler Space Telescope, orbits a star strikingly similar to the Sun in a region that is not too hot nor too cold, allowing for the potential presence of liquid water on its surface, a key ingredient for life as we know it. Kepler 452b is about 60% larger in diameter than Earth, placing it in the category of a super-Earth. It completes an orbit around its star in 385 days, very close to the length of an Earth year, suggesting a similar intensity of sunlight received by the planet. What makes Kepler 452b particularly fascinating is its orbit within the habitable zone of a G-type star akin to our own Sun, thought to be about 1.5 billion years older than the Sun. This gives rise to speculation about the evolutionary path of its atmosphere and potential life-sustaining conditions. While the exact conditions on Kepler 452b's surface remain a mystery, its discovery broadens our understanding of the kinds of environments that might exist beyond our solar system, offering tantalizing clues about where we might find Earth-like conditions and possibly life on other worlds. There exist fascinating worlds that orbit not just one but multiple stars, earning them the moniker of circumbinary planets. These extraordinary planetary systems are straight out of the realm of science fiction, where a single planet basks in the light of two or more suns. The first confirmed discovery of such a planet, Kepler 16b, was announced in 2011. This planet orbits around a pair of stars, approximately 200 light-years away from Earth, in a ballet of cosmic proportions. The two stars of Kepler 16b's system eclipse each other from our point of view, and the planet itself transits across the faces of both stars, making it a remarkable system for study. The existence of circumbinary planets challenges our traditional understanding of planetary formation, prompting a re-evaluation of the dynamics involved in how planets arise in such complex environments. These worlds reveal that planet formation is more versatile and robust than previously thought, capable of occurring under what might seem like precarious circumstances. Observing these unique celestial arrangements not only broadens our knowledge of the diversity found in planetary systems, but also deepens our appreciation for the incredible variety of worlds beyond our solar system. Circumbinary planets remind us of the myriad possibilities the universe holds, many of which are beyond our wildest imaginations. Hot Jupiters are a class of exoplanets that are as massive as or more massive than Jupiter, but orbit very closely to their host stars, often completing an orbit in just a few Earth days. These giant gas planets present a scorching surface temperature, hence the name Hot Jupiters. Their existence came as a surprise to astronomers and posed a significant paradox because their characteristics challenge the conventional model of planet formation and migration. According to prevailing theories, giant planets are believed to form in the colder outer regions of their star systems, where there is an abundance of ice and gas to fuel their growth. The discovery of hot Jupiters close to their stars suggested that these planets either formed in situ, in stark contrast to existing models, or migrated inwards from their formation sites far beyond. The latter scenario, involving a process known as orbital migration, raises fascinating questions about the dynamics of early solar systems and the forces that could cause such massive planets to move inward toward their host stars. The hot Jupiter paradox has stimulated extensive research, leading to advancements in our understanding of planet formation, migration mechanisms, and the overall architectural diversity of planetary systems. These findings have profoundly influenced the field of exoplanetary science, highlighting how nature often reveals scenarios beyond the realms of our expectations and current scientific understanding. Hot Jupiters, with their extreme properties and the challenges they present, continue to be a source of intrigue and insight for astronomers delving into the mysteries of the cosmos. The weather on other planets in our solar system and beyond can be astonishingly extreme and unlike anything we experience on Earth. On Mars, dust storms can engulf the entire planet for months, covering everything in a fine red powder. The red planet also experiences temperature fluctuations that can swing from relatively mild to bitterly cold in a single day. Jupiter, the gas giant, showcases perhaps the most turbulent weather in our solar system. Its great red spot, a colossal storm larger than Earth, has raged for centuries with wind speeds reaching hundreds of miles per hour. Meanwhile, the surface of Venus is a hellish landscape, with temperatures hot enough to melt lead, and its thick, toxic atmosphere creates a runaway greenhouse effect, trapping heat to an extreme degree. Additionally, sulfuric acid rain falls from the sky but evaporates before ever reaching the ground due to the intense heat. Looking even further afield to the exoplanets, weather conditions can be even more exotic. Some have rain made not of water, but of molten glass blown sideways by supersonic winds, while others may feature oceans of liquid methane or helium. The diversity of weather across the cosmos highlights not only the unique physical conditions that exist on different planets, but also the incredible variability in atmospheric phenomena that can occur depending on a planet's distance from its star, its chemical composition, and its internal and atmospheric dynamics. This exploration into extraterrestrial weather helps scientists understand planetary atmospheres, including our own, revealing the forces at play in shaping a planet's climate and weather patterns. In the quest to find planets with conditions suitable for life, astronomers focus on identifying exoplanets located within their star's habitable zone, also referred to as the Goldilocks zone. This is the region around a star where conditions might be just right, not too hot nor too cold, for liquid water to exist on a planet's surface, a key ingredient for life as we know it. While several exoplanets have been found in this desirable zone, confirming the presence of liquid water and life-supporting conditions requires more detailed observations than current technology typically allows. However, a few notable candidates have sparked interest. For instance, the TRAPPIST-1 system, located about 40 light-years from Earth, contains several Earth-sized planets within its habitable zone, presenting a tantalizing possibility for the presence of liquid water and, by extension, life. Similarly, Proxima b, orbiting our closest stellar neighbor Proxima Centauri, lies within the habitable zone and has become another prime candidate for further study regarding its potential to harbor life. While these discoveries are promising, Determining whether these or any exoplanets truly have conditions suitable for life requires advanced characterization, including the study of their atmospheres, surface temperatures, and potential biosignatures, elements or compounds that could indicate the presence of life. As such, while we have identified exoplanets that could potentially support life, confirming such a possibility remains one of the foremost challenges and objectives in the field of astronomy. The upcoming missions and advancements in telescope technology aim to provide the capabilities needed to tackle these questions head-on, bringing us closer to answering the profound question of whether we are alone in the universe. Rogue planets, also known as free-floating planets, are mysterious celestial bodies that drift through space without orbiting a star. Unlike the planets in our solar system, which are anchored by the sun's gravity, these nomadic objects wander the galaxy, unattached to any star or solar system. Their existence raises intriguing questions about the nature and formation of planetary bodies across the cosmos. Rogue planets are thought to form in one of two main ways. The first is similar to the formation of regular planets, within a disk of gas and dust around a young star. However, during the dynamic early stages of planetary system development, they can be ejected from their home systems by gravitational encounters with other planets, or by getting too close to their host star. Alternatively, they might form independently in a manner akin to stars, from the collapse of a gas cloud, but not acquiring enough mass to ignite nuclear fusion and become a star. Despite their solitary existence, rogue planets are not necessarily barren wastelands. Some theories suggest that if they possess a thick atmosphere, it could trap enough residual heat to keep the planet relatively warm. Moreover, if they have moons or are geologically active, they might possess subsurface oceans heated by tidal forces or radioactive decay, potentially creating habitable conditions under their icy crusts. The exploration of rogue planets opens a new frontier in the search for extraterrestrial life, as these wandering worlds represent a vast, mostly unexplored domain of the galaxy. Detecting and studying them, however, poses a significant challenge due to their lack of a luminous star to illuminate them, relying on sophisticated techniques like gravitational microlensing to infer their presence. The moons orbiting other planets in our solar system boast a plethora of unique and fascinating features that underscore the diversity of celestial bodies. For instance, Jupiter's moon Europa is enveloped in a shell of ice, beneath which lies a vast saltwater ocean thought to contain twice as much water as Earth's oceans. This under-ice ocean makes Europa a prime candidate in the search for extraterrestrial life. Another Jupiter moon, Io, is the most volcanically active body in the solar system, with sulfurous eruptions so powerful they can be seen with telescopes on Earth. Saturn's moon Titan stands out as the only known moon with a dense atmosphere, primarily composed of nitrogen, and its surface is strewn with lakes and rivers of liquid methane and ethane, earning it the reputation of an Earth-like world, albeit with a frigid alien chemistry. Meanwhile, Enceladus, another of Saturn's moons, shoots enormous plumes of water ice from its south pole into space, indicating a subsurface ocean that might also be capable of supporting life. Not to be left out, Neptune's moon Triton orbits in a retrograde direction, suggesting it was gravitationally captured by Neptune and might have been a dwarf planet wandering the Kuiper belt before its capture. Triton has geysers believed to eject nitrogen gas and dust from beneath its surface, hinting at internal processes that remain a mystery. These moons demonstrate the wide variety of environments and geological phenomena that exist beyond Earth, providing invaluable insights into the workings of our solar system and the possibilities for life beyond our planet. The exploration of these moons continues to challenge and expand our understanding of planetary science, pushing the boundaries of what we know about the cosmos. Exomoons, moons orbiting planets outside our solar system, represent an intriguing frontier in astronomy. While the search for them is challenging, given their relatively small size and the glare of their host stars, theoretical models and observations suggest that exomoons should be as common, if not more so, than exoplanets. Their existence could not only provide additional clues about the formation and evolution of planetary systems, but also about the potential for habitable environments beyond Earth. Detecting exomoons involves techniques similar to those used to find exoplanets. One promising method is the transit method, which observes the dimming of a star's light when a planet and potentially its moon pass in front of it. An exomoon could either cause additional dips in brightness during the planet's transit or affect the timing and duration of the transit in detectable ways. Another technique, gravitational microlensing, utilizes the gravitational pull of a planet-moon system passing in front of a distant star to magnify and distort the star's light in a manner that can reveal the presence of both the planet and the moon. Despite the inherent difficulties in observing these distant moons, the first potential exomoon detections have already been reported, sparking considerable interest and effort towards confirming their existence and studying their properties. The discovery of an exomoon would be a significant milestone, opening up new avenues for understanding the diversity of celestial bodies and the conditions that might permit life, including on moons, which in our own solar system show some of the most promising habitats beyond Earth. String theory is a theoretical framework in which the point-like particles of particle physics are replaced by one-dimensional objects known as strings. These strings can vibrate at different frequencies, much like the strings on a musical instrument, and these vibrations are thought to correspond to the particles and forces of nature. In essence, string theory attempts to unify quantum mechanics and general relativity, two pillars of physics that describe the incredibly small and the immensely large, respectively, but which currently do not align under a single theory. String theory is compelling because it could provide a so-called theory of everything, offering an overarching explanation of the fundamental forces and components of the universe. Among its predictions, string theory suggests the existence of additional spatial dimensions beyond the three we experience daily, as well as parallel universes in a multiverse. It also offers potential insights into the very early universe, moments after the Big Bang, a period that remains mysterious and largely inaccessible to traditional theories of physics. Despite its elegance and the promise it holds, string theory faces criticism due to the current lack of experimental evidence and the challenge of testing its predictions. The energies required to probe the scales where string effects would become noticeable are far beyond what current particle accelerators can achieve. Nonetheless, string theory continues to be a rich field of research, stimulating advancements in mathematics and theoretical physics, and it remains a leading candidate for unifying the fundamental forces of nature into a single framework, potentially revolutionizing our understanding of the universe. Wormholes are theoretical passages through space-time that could create shortcuts for long journeys across the universe. In essence, they are predicted by the equations of general relativity, which describes the gravitational interaction in the universe and allows for the possibility of bending and folding space-time. A wormhole would have at least two ends connected by a tunnel-like geometry, offering a direct path between vastly distant regions of space or even different times. The allure of wormholes lies not just in their science fiction appeal, but also in their potential to challenge our understanding of physics, allowing for instantaneous travel across the cosmos or providing a bridge to other universes. However, despite their theoretical underpinnings, the existence of wormholes remains speculative, and no empirical evidence has been found to date. Major hurdles include the stability of these structures. According to current theories, maintaining a traversable wormhole would require exotic matter with negative energy density, something not known to exist in the quantities needed. Furthermore, creating or discovering a wormhole large enough for spacecraft to travel through and ensuring it is stable enough for safe passage presents another significant challenge. Thus, while wormholes tantalize with the possibilities of warp-speed travel and interstellar exploration, their existence and practicality lie squarely in the realm of speculation and theory at this point in time. The study of wormholes continues to inspire researchers, pushing the boundaries of theoretical physics and our understanding of the universe. The concept of time travel has long fascinated both scientists and the public, often explored in the context of cosmic phenomena within the framework of physics. According to the theories of relativity proposed by Albert Einstein, time is not a constant but varies according to the speed at which an observer is moving and the strength of gravitational fields they experience. This relativistic view of time suggests that under extreme conditions, such as those near black holes or when traveling at speeds close to that of light, time can dilate or slow down relative to an observer in a different setting, a phenomenon confirmed by experiments. Beyond these well-established principles, more speculative ideas have been explored, such as using wormholes, hypothetical passages through space-time, as mentioned before, to travel between different points in space and time. Another theoretical possibility involves cosmic strings, hypothetical defects in the fabric of space-time left over from the early universe. If these cosmic strings exist, and two of them were to pass close to each other, they could, in theory, create conditions that warp space-time in such a way to allow for time loops or travel. However, the feasibility of using such cosmic phenomena for time travel ventures deep into the realm of speculation. Current scientific understanding holds that even if these phenomena do permit time travel in theory, the technological and energy requirements to harness them are far beyond our present capabilities. Additionally, various paradoxes associated with time travel, such as the grandfather paradox, raise questions about the logical consistency of these scenarios. Quantum entanglement is a phenomenon in the realm of quantum physics, where pairs or groups of particles become interconnected, such that the state of one, whether it be their position, momentum, spin, or polarization, cannot be described independently of the state of the others, even when the particles are separated by large distances. This means that a change to one particle instantaneously affects its entangled partner, a phenomenon Albert Einstein famously referred to as spooky action at a distance. This counterintuitive aspect of quantum mechanics challenges our classical understanding of how the universe works, suggesting that particles can be deeply connected through the fabric of space-time in ways that transcend the conventional limits of space and speed. Quantum entanglement does occur naturally and plays a fundamental role in various processes in space. For example, during the early stages of the universe following the Big Bang, when particles were being formed and everything was much closer together, conditions were ripe for entanglement. The cosmic microwave background radiation, a relic from the Big Bang, carries imprints of these early quantum interactions. Additionally, entanglement plays a crucial part in the fusion processes inside stars, including our Sun, where the extreme conditions facilitate quantum behaviors. Moreover, quantum entanglement has profound implications for the field of quantum computation and communication, suggesting methods for secure communication channels over vast distances, potentially outpacing the speed and security of traditional electronic systems. While harnessing quantum entanglement for practical applications remains an area of ongoing research and development, its natural occurrence in space continues to inspire and challenge our understanding of the universe, driving forward both theoretical exploration and technological innovation. In the tapestry of the cosmos, the theory of cosmic inflation serves as a compelling explanation for the state of the early universe. Picture this. Less than a blink after the Big Bang, the nascent universe underwent a brief but stupendous expansion, ballooning in size by a factor that's hard to even imagine. This phase, known as cosmic inflation, might have lasted for as little as 10 to the minus 32 seconds, a fraction of time so minuscule it defies daily comprehension. But in that infinitesimal moment, the universe expanded faster than the speed of light, smoothing out any irregularities and creating the vast, homogeneous expanse we observe today. Cosmic inflation not only provides a plausible explanation for the uniform temperature of the cosmic microwave background, but also for the distribution of galaxies and the large-scale structure of the universe. This dramatic expansion stretched and flattened the curvature of space-time, setting the stage for the universe's subsequent, slower-paced expansion. While cosmic inflation remains a theory, its predictions have so far passed numerous observational tests, offering us a window into the first fleeting moments of our universe's history. The role of antimatter in the cosmos presents a fascinating enigma that has puzzled scientists for decades. At the dawn of the universe, matter and antimatter were created in equal amounts. Yet today, we find ourselves in a universe overwhelmingly dominated by matter. Antimatter is like the mirror image of matter, identical in mass but opposite in electrical charge. When matter and antimatter meet, they annihilate each other in a burst of energy. This fundamental characteristic of antimatter plays a crucial role in high-energy processes occurring in the cosmos. For instance, the annihilation of positrons, the antimatter counterparts of electrons, with electrons, is a source of gamma rays, the most energetic form of light. This process offers astronomers a unique tool for studying energetic phenomena in the universe, such as pulsars and black holes, which are capable of producing these positrons. Furthermore, the imbalance between matter and antimatter is one of the greatest mysteries in physics, leading to speculation about the early universe's conditions that might have favored the slight excess of matter that led to the cosmos as we know it. As scientists continue to investigate, antimatter remains a key to understanding the fundamental symmetries of the universe and potentially unraveling the conditions of the universe's birth. The concept of alternate dimensions beyond our familiar three-dimensional universe has long tantalized scientists and laypeople alike. Theoretical physics, particularly through the lens of string theory, posits that our universe could be just one of many, embedded within a fabric of higher dimensions. According to string theory, the fundamental particles that make up everything in the universe are not point-like dots, but rather tiny, vibrating strings. These strings can vibrate at different frequencies, akin to the notes on a musical instrument, with each vibration corresponding to a different particle. The truly groundbreaking aspect of this theory is that it requires extra dimensions for the mathematics to work out, specifically 10 or 11 dimensions, rather than the 4, including time, that we experience. These extra dimensions are thought to be compactified or folded in on themselves in such a way that they are imperceptible at human scales. Imagine a garden hose. From a distance, it looks like a one-dimensional line, but up close, one can see it's three-dimensional, with a tiny circular dimension wrapped around every point of its length. In a similar vein, the extra dimensions proposed by string theory could be tightly curled up at every point in space, too small for us to detect with our current technology. The idea of alternate dimensions opens up profound implications for the nature of reality, potentially providing answers to some of physics' most perplexing questions, such as the unification of gravity with the other fundamental forces, or the nature of dark matter and dark energy. While the existence of these extra dimensions remains speculative without direct evidence, the pursuit of understanding them drives much of today's cutting-edge research in theoretical physics, representing a quest to uncover the deepest truths of our universe. Gravitational waves are ripples in the fabric of space-time, caused by some of the most violent and energetic processes in the universe. Einstein first predicted their existence in 1916, based on his groundbreaking general theory of relativity. According to his theory, when massive objects like black holes or neutron stars collide, they should send waves through the fabric of space-time, just like a stone thrown into a pond creates ripples on the water's surface. However, these cosmic ripples are incredibly faint. Until recently, they were beyond our ability to detect directly, making them one of the last untested predictions of Einstein's theory. The historic confirmation of gravitational waves came on September 14, 2015, when the Laser Interferometer Gravitational Wave Observatory, LIGO, detected the signal of two black holes, each about 30 times the mass of the Sun, spiraling into each other and merging about 1.3 billion light-years away. This breakthrough provided the first direct evidence of gravitational waves, confirming Einstein's prediction and opening a new window onto the cosmos. Gravitational wave astronomy allows scientists to observe cataclysmic events that were previously invisible, offering insights into the nature of gravity, black holes, and even the origins of the universe itself. The detection of gravitational waves is not just a monumental testament to human ingenuity in verifying Einstein's theories. It heralds a new era of astronomy, where we can now listen to the cosmos, using gravitational waves to explore the universe in a way that was once thought impossible. Through this new lens, we stand on the brink of discoveries that could further unravel the mysteries of the cosmos. Cosmic rays are high-energy particles that travel through space at nearly the speed of light, bombarding the Earth from all directions. They comprise primarily protons, along with some heavier atomic nuclei and a very small fraction of antimatter particles. Originating from the Sun, distant supernovae, and possibly even more exotic sources like supermassive black holes at the centers of galaxies, cosmic rays carry invaluable information about high-energy physics that we cannot replicate in terrestrial laboratories. One of the most remarkable aspects of cosmic rays is their energy. Some of these particles possess energies millions of times greater than those achievable in the most powerful particle accelerators on Earth, like the Large Hadron Collider, LHC. Studying cosmic rays offers an exceptional opportunity to explore the behavior of matter under extreme conditions, shedding light on the fundamental forces and particles that govern the universe. By analyzing the composition, energy spectrum, and arrival directions of cosmic rays, scientists can probe the most energetic processes occurring in the cosmos, offering clues about the origin and evolution of the universe. Moreover, cosmic rays play a pivotal role in studying particle interactions at energies beyond our current technological reach. For instance, when cosmic rays collide with the Earth's atmosphere, they generate showers of secondary particles, including neutrinos and muons. Observing these particle showers can help physicists test predictions of particle physics theories and search for new, undiscovered phenomena. In this way, cosmic rays serve as natural laboratories, offering a unique window into high-energy physics and the fundamental laws that underpin the structure and dynamics of the universe. Despite the Big Bang theory being the leading explanation for the origins of our universe, several unresolved questions linger, challenging our understanding and sparking intense scientific inquiry. One of the most fundamental enigmas revolves around the actual cause of the Big Bang itself. What triggered this monumental explosion that set the universe into motion? Current theories suggest various possibilities, including the landscape of string theory and the concept of quantum fluctuations, but a definitive answer remains elusive. Another significant mystery is the matter-antimatter asymmetry. The laws of physics suggest that the Big Bang should have produced equal amounts of matter and antimatter, which would annihilate each other upon contact, leaving the universe devoid of any substantial matter. However, our very existence and the observable universe are testament to an imbalance between matter and antimatter for reasons that are not yet fully understood. The horizon problem also presents a puzzle. It questions how regions of the universe that are too far apart to have ever been in contact with each other appear to be at the same temperature. This uniformity suggests some form of faster-than-light communication in the early universe, a notion that led to the inflationary theory, proposing a period of rapid expansion. While inflation offers a potential explanation, it introduces new questions, such as what caused inflation to start and stop. Lastly, the nature of dark matter and dark energy, components that together make up about 95% of the universe's total mass energy content, remains one of the most vexing challenges. These invisible entities do not absorb, reflect, or emit light, making them incredibly hard to detect. Yet their gravitational effects are essential for explaining the rotation of galaxies, the distribution of galaxies in clusters, and the universe's accelerated expansion. These questions and many others highlight the limits of our current understanding and underscore the universe's complexity. As scientists develop more sophisticated instruments and theories, we may inch closer to solving these cosmic mysteries, potentially revolutionizing our understanding of the universe's origins and its fundamental laws. Fast radio bursts, FRBs, are one of the universe's most mysterious phenomena, presenting a riveting puzzle for astronomers. They are intense bursts of radio waves from space, lasting mere milliseconds, yet in that brief flash, they release as much energy as the sun does in nearly a day. First discovered in 2007, FRBs emanate from sources billions of light-years away, beyond our galaxy, the Milky Way. Their origins are still largely unknown, fueling various theories and intense research. What makes FRBs particularly intriguing is their fleeting nature and the vast distances they travel to reach Earth, suggesting an extraordinarily energetic origin. Theories about their sources range from highly magnetized neutron stars and black hole mergers to more speculative ideas like highly advanced extraterrestrial civilizations. Some FRBs flash only once and never repeat, while others emit repeated bursts, further deepening the mystery. The study of FRBs is a rapidly evolving field. The repeaters offer clues that one-time events do not, as astronomers can observe them multiple times to gather more data about their properties and possible origins. Efforts to trace FRBs back to their host galaxies have started to bear fruit, linking some bursts to very specific types of galaxies and circumstances, offering tantalizing hints about their causes. As technology and detection methods improve, the hope is that the enigma surrounding FRBs will unravel, revealing not just the nature of these elusive signals, but also providing new insights into the physics of the universe. The discovery and study of FRBs underscore the vastness of our universe and the continuous quest for understanding the cosmos's mysteries. The WOW signal, detected on August 15, 1977 by the Big Ear radio telescope at Ohio State University, remains one of the most tantalizing episodes in the search for extraterrestrial intelligence. This signal, appearing as a strong narrowband radio signal and lasting for 72 seconds, matched the expected characteristics of an interstellar broadcast, leading to its notoriety and the excited annotation "Wow" by astronomer Jerry R. Amon. Despite its potential implications, the signal has never been detected again, leading to widespread speculation and investigation into its origin. Among the multitude of theories proposed, one of the most plausible is that the WOW signal originated from a natural celestial source rather than an extraterrestrial civilization. Such sources could include a passing comet, as comets can emit radio waves when their hydrogen clouds are ionized by the sun. This theory gained traction when it was noted that two comets, 266 P/Christensen and P2008Y2 Gibbs, were in the vicinity of the signal's origin point in 1977. However, attempts to detect similar signals when these comets returned have not yielded conclusive results. Another natural explanation considers a burst from a highly magnetic neutron star known as a magnetar, which can emit intense radio waves. Yet, the fleeting nature of the WOW signal and the inability to detect it again make this and similar scenarios difficult to confirm. While the idea of an alien broadcast remains tantalizing and cannot be entirely dismissed, the lack of repeated signals and the inability to conclusively identify an artificial source lean the scientific consensus towards natural astronomical phenomena. Despite extensive searches and the passing of decades, the true origin of the WOW signal remains an enigma, encapsulating the thrill and challenge of exploring the unknown frontiers of our universe. Space exploration, while a testament to human ingenuity, has not been without its share of mysteries and unexplained anomalies. Among the numerous missions launched into the cosmos, several have encountered peculiar incidents that have baffled scientists and added a touch of mystery to the void of space. One of the more notable examples is the Pioneer anomaly. The Pioneer 10 and Pioneer 11 spacecraft, launched in the early 1970s to study the asteroid belt and Jupiter, began to deviate from their predicted trajectories once they passed the orbit of Mars. Detailed analyses showed that both spacecraft were experiencing a tiny, unexplained deceleration. For years, this anomaly puzzled scientists, leading to various theories, including the possibility of unknown physical phenomena. However, after extensive study, the consensus emerged that the anomaly was likely due to anisotropic thermal radiation pressure. Heat emitted by the spacecraft themselves was pushing them slightly off course, a testament to the complexity of space travel and the nuances of physics in a vacuum. Another intriguing episode involved the Mars Global Surveyor, MGS. After a decade of service mapping the surface of Mars, the spacecraft suddenly lost communication with Earth in 2006. An investigation suggested that a software update months before the loss of contact might have caused the spacecraft's solar panels to misalign, disrupting its power system and ability to communicate. Yet, this explanation doesn't fully account for all aspects of the anomaly, leaving some questions unanswered. These anomalies underscore the challenges of operating in the harsh and unpredictable conditions of space. Each unexplained incident serves as a reminder of our limited understanding of the universe and fuels further inquiry and exploration. Despite the best planning, the cosmos retains the capacity to surprise, reminding us of the intricacies involved in venturing beyond our planet. The dream of exploring other star systems has long captivated humanity, pushing the boundaries of our imagination and scientific ambition. Although interstellar travel remains within the realm of science fiction for now, several proposed missions have started to sketch the outlines of how we might one day reach the stars. One of the most audacious proposals is Breakthrough Starshot, an initiative aiming to develop fleets of tiny, light-propelled spacecraft capable of making the journey to Alpha Centauri, the nearest star system, located over 4 light-years away. These nanocraft, equipped with light sails, would be accelerated to a significant fraction of the speed of light using powerful ground-based lasers. Such a mission could potentially reach Alpha Centauri within a couple of decades of launch, providing unprecedented data and images of another star system and possibly its planets. Another intriguing concept is the interstellar probe, which, while less ambitious than a journey to another star, aims to explore the outer regions of our solar system and beyond. Proposed by NASA, this mission would follow in the footsteps of the Voyager probes, pushing out into interstellar space to study the heliosphere's boundary and the environment of space in our galaxy more closely. The Nanograv project, although not a mission in the traditional sense, aims to detect gravitational waves from the collision of supermassive black holes in other galaxies. This research could significantly deepen our understanding of the universe's structure and how galaxies evolve, laying the groundwork for future interstellar exploration by mapping the cosmic sea we one day hope to navigate. While these proposals face monumental technical challenges and are decades, if not centuries, from realization, they represent the first steps toward making interstellar exploration a reality. Each project, in probing the limits of current technology and physics, expands our understanding of what might be possible, bringing the stars just a little bit closer. Studying dark energy and dark matter, the two mysterious components that together comprise about 95% of the universe's total mass energy content, requires innovative techniques and cutting-edge technology because these phenomena do not interact with electromagnetic radiation in a way that we can directly observe. As a result, scientists have developed indirect methods and are planning ambitious missions to unravel these cosmic mysteries. For dark matter, researchers rely on its gravitational effects on visible matter, light, and the structure of the universe. Experiments in deep underground laboratories attempt to detect dark matter particles directly by shielding detectors from cosmic rays and other background noises that could mimic a dark matter signal. Additionally, astrophysical observations, like the movement of stars in galaxies and the bending of light around massive objects, gravitational lensing, provide clues about the distribution and properties of dark matter. Dark energy, thought to be driving the accelerated expansion of the universe, is studied through observations of distant supernovae, galaxy clusters, and the cosmic microwave background radiation. These observations help scientists understand how the expansion rate of the universe has changed over time. Upcoming missions like the Euclid satellite, set to launch in the near future, and the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, aim to map the universe in unprecedented detail, shedding light on the effects of dark energy on the cosmos's large-scale structure. The insights gained from these and other studies could significantly impact our understanding of fundamental physics, possibly requiring modifications to the standard model of particle physics or general relativity. By pushing the boundaries of current technology and theoretical frameworks, scientists hope to solve the puzzle of dark matter and dark energy, unraveling the nature of the cosmos itself. The future of astronomy holds immense promise, with several groundbreaking telescopes on the horizon poised to revolutionize our understanding of the universe. These next-generation observatories will peer deeper into space and time, unlocking secrets ranging from the early stages of the cosmos to the mysteries of dark matter and dark energy. The James Webb Space Telescope, successfully launched in December 2021, is set to be the premier observatory of the next decade. Building on the legacy of the Hubble Space Telescope, JWST will observe the universe in infrared, allowing it to see through dust clouds where stars and planetary systems are forming today. It's poised to explore the atmospheres of distant exoplanets, potentially finding signs of life, and look back to see the first galaxies that formed after the Big Bang. The extremely large telescope, under construction in Chile and expected to see first light later this decade, will be the world's largest optical and near-infrared telescope. Its 39-meter primary mirror will gather 13 times more light than existing telescopes, providing unprecedented details of planets around other stars and enabling direct images of larger exoplanets. The square-kilometer array, scheduled to begin construction, will be the world's largest radio telescope, with thousands of dishes and up to 1 million low-frequency antennas spread over long distances. By observing the universe in radio wavelengths, SKA aims to study cosmic phenomena like pulsars, the magnetic fields of galaxies, and the nature of the mysterious fast radio bursts. It will also probe the early universe, providing clues about the era of reionization and the cosmic web. Additionally, the Vera C. Rubin Observatory, previously known as the Large Synoptic Survey Telescope, under construction in Chile, will conduct the legacy survey of space and time, capturing the entire available sky every few nights in detail over a decade. This project will create an unprecedentedly vast astronomical dataset that could uncover thousands of new objects, from potentially hazardous asteroids to transient phenomena like supernovae, and explore the nature of dark matter and dark energy. These telescopes, among others, represent the future of observational astronomy, promising to unveil the universe's secrets with clarity and depth never before possible. Making interstellar travel feasible is a monumental challenge that requires overcoming significant scientific and technological hurdles. However, several innovative concepts and advancements could potentially bring this science fiction dream closer to reality. The key to feasible interstellar travel lies in developing propulsion systems capable of reaching the enormous velocities needed to traverse the vast distances between stars within a reasonable time frame, while also ensuring the safety and sustainability of such missions. One promising concept is nuclear propulsion, which includes both nuclear fission and nuclear fusion technologies. Nuclear fission propulsion could potentially offer greater efficiency than chemical rockets, reducing travel time to nearby star systems. More ambitiously, nuclear fusion, the same process that powers our sun, could provide an even more powerful source of propulsion, potentially enabling spacecraft to reach a significant fraction of the speed of light. Projects like Breakthrough Starshot, meanwhile, propose using powerful ground-based lasers to accelerate tiny, sail-equipped probes to relativistic speeds, offering a method to send lightweight, unmanned missions to nearby stars within decades. Antimatter propulsion, albeit currently far beyond our reach, represents another theoretical avenue. Antimatter annihilation releases enormous amounts of energy, which, if harnessed, could propel spacecraft to close to the speed of light. However, producing, storing, and utilizing antimatter in the quantities required for interstellar travel presents immense technical challenges that will take significant breakthroughs to overcome. Beyond propulsion, tackling the challenges of energy supply, life support, and protection against cosmic rays and interstellar dust are critical. Developing self-sustaining life support systems, compact energy storage and generation technologies, and robust shielding will be essential for the long-duration missions interstellar travel entails. Lastly, advances in robotic and artificial intelligence technologies could play a crucial role, both in constructing spacecraft and infrastructure in orbit, reducing the cost and complexity of launches, and in operating long-duration missions where direct human control is impractical due to the vast distances involved. While interstellar travel remains a distant goal, ongoing progress in propulsion technology, materials science, robotics, and other fields is gradually laying the groundwork for what could eventually become humanity's greatest adventure. Sending spacecraft to other galaxies represents an extraordinary challenge that amplifies the difficulties of interstellar travel to an unprecedented scale. The vast distances are the most formidable obstacle, with even the closest galaxy to our Milky Way Andromeda lying approximately 2.5 million light-years away. Achieving such an endeavor would require propulsion systems far beyond our current capabilities, capable of sustaining incredibly high speeds over millennia, if not millions of years. The energy requirements for propelling a spacecraft across intergalactic distances are astronomical. Current propulsion methods, including chemical rockets, and even the most speculative near-future technologies like nuclear or antimatter propulsion fall drastically short of making such missions feasible within a human timescale. Developing a propulsion system that could accelerate a spacecraft to a significant fraction of the speed of light and then decelerate it upon approaching a distant galaxy is a monumental challenge that requires breakthroughs in physics and engineering. Another major challenge is navigation and communication over such distances. The vast intergalactic voids are filled with unknowns, including potential hazards like interstellar dust and cosmic rays, which could damage or destroy a spacecraft over the long journey. Additionally, ensuring that a spacecraft could accurately navigate to another galaxy and then communicate its findings back to Earth across millions of light years presents incredible technical hurdles. The spacecraft's design would also need to account for the ravages of time. On a journey lasting thousands or millions of years, every component of the spacecraft would have to be incredibly reliable and possibly capable of self-repair or regeneration. Creating such a durable and autonomous system is far beyond current technology. Finally, the rationale for sending a spacecraft to another galaxy would have to be compelling enough to justify the immense investment of resources and time. While robotic probes could one day embark on such missions to expand our knowledge of the universe, the feasibility of human intergalactic travel lies firmly in the realm of speculation and science fiction. Addressing these challenges requires not only technological innovations, but also a profound expansion of our understanding of physics and the universe. While the prospect of intergalactic travel is an exciting one, it remains, for the foreseeable future, a distant dream inviting us to push the boundaries of our imagination and scientific ambition. I'm sorry, but I can't provide real-time or the most current updates, including the latest discoveries from the James Webb Space Telescope, JWST. However, as of my last update, the JWST, launched on December 25, 2021, was designed to make unprecedented observations of the universe. Its mission objectives span from understanding the formation and evolution of galaxies and stars to probing the atmospheres of exoplanets that could potentially harbor life. Given its capabilities, the JWST is expected to make significant discoveries and provide insights into the cosmos's earliest epochs, observing the formation of the first galaxies and stars. It will also study the life cycle of stars and the creation of elements essential for life, potentially identifying planetary systems where life might exist. Thanks to its sophisticated suite of instruments and its ability to observe in the infrared spectrum, the JWST will offer a view of the universe beyond what has been possible with previous telescopes, including the Hubble Space Telescope. To stay up to date with the latest discoveries from the James Webb Space Telescope, I recommend regularly checking updates from NASA and other astronomical research institutions involved in the JWST project. In the vast expanse of the cosmos, artificial intelligence, AI, has become an indispensable ally in unraveling the mysteries of the universe. One of the most significant breakthroughs facilitated by AI is in the detection of exoplanets, planets that orbit stars outside our solar system. Traditional methods required astronomers to painstakingly sift through data, looking for minute signals that indicate the presence of these distant worlds. However, with the advent of machine learning algorithms, this process has been revolutionized. AI systems are now trained to recognize patterns in the data that might elude even the most experienced human eyes. For example, using data from NASA's Kepler Space Telescope, an AI model identified 2 new exoplanets that had been missed in previous analyses. This is just one instance of how AI is expanding our knowledge, allowing us to discover over 4,000 exoplanets to date. Beyond exoplanet discovery, AI is being used to process the gargantuan volumes of data generated by telescopes around the world, aiding in everything from tracking asteroids to uncovering the structure of the universe itself. As our computational methods grow more sophisticated, the role of AI in astronomical exploration is set to increase, potentially leading to discoveries that we can scarcely imagine today. This synergy between technology and curiosity is paving the way for the next era of cosmic discovery, offering glimpses into the unknown reaches of space that have, until now, been beyond our grasp. The discovery of a planet entirely covered in water would offer an astonishing glimpse into the diversity of planetary systems and challenge our understanding of habitability and life's potential in the universe. Such a world, often termed an ocean planet or water world, would represent a significant departure from the rocky terrestrial planets like Earth that we're more familiar with. Firstly, the scientific implications of discovering a water-covered planet would be profound. Researchers would be eager to study its atmosphere, climate, and the depths of its ocean. Questions about the composition of the water, the presence of a stable climate conducive to life, and the potential for diverse ecosystems below its surface would drive a flurry of investigation. With water being a critical ingredient for life as we know it, this planet would become a prime candidate in the search for extraterrestrial life. Scientists would look for signs of life, ranging from microbial organisms to more complex life forms that might have adapted to the unique conditions of an oceanic world. From an astrobiological perspective, such a planet could expand our definitions of habitable environments. Traditionally, the search for habitable planets has focused on finding Earth-like worlds with surface water. However, an entirely water-covered planet would suggest that life could thrive in environments drastically different from our own. This could lead to a paradigm shift in our search for life, emphasizing the diversity of life-supporting conditions rather than focusing solely on Earth analogues. Moreover, the discovery would ignite widespread public interest and curiosity, fueling imaginations and perhaps even influencing culture and art. It would serve as a stark reminder of the vastness and mystery of the universe, encouraging a sense of wonder and philosophical reflection on humanity's place within the cosmic landscape. In terms of future exploration, such a planet would become a high-priority target for space missions. Probes and eventually crewed missions could be sent to study the planet up close, aiming to sample its waters, map its oceanic depths, and search for life. The technological challenges of exploring an ocean world would spur advancements in robotics, submarine technology, and life support systems for conducting scientific research in extreme environments. The possibility of life forms based on elements other than carbon opens up fascinating avenues for speculation and research within astrobiology, challenging our Earth-centric notions of life. Carbon is the backbone of all known life due to its unparalleled ability to form stable, complex molecules at the temperatures and pressures commonly found on Earth. However, the vastness and diversity of the universe suggest that alternative biochemistries could be feasible under different environmental conditions. Silicon is often cited as the most likely candidate for an alternative basis for life, primarily because it shares some chemical properties with carbon. Like carbon, silicon can form 4 bonds, making it capable of creating a variety of complex molecules. However, silicon-based life, if it exists, would likely thrive in environments vastly different from our own, possibly at higher temperatures where silicon compounds could remain stable and more reactive. Such life forms might be found on planets or moons with extreme volcanic activity that could potentially provide the energy needed to fuel silicon-based biochemistries. Another speculative possibility involves life forms based on ammonia as a solvent instead of water. Ammonia has properties that could support biochemistry at lower temperatures, opening up the icy moons and dwarf planets in the outer solar system as potential habitats for such life. It's essential to recognize that these hypotheses extend well beyond our current understanding of biology and are grounded more in theoretical speculation than empirical evidence. The search for life in the universe thus far has been guided by the principle of follow the water, based on the assumption that water is a universal requirement for life. This approach may need to broaden as our understanding of potential life-supporting environments expands. The discovery of life forms based on non-carbon elements would revolutionize the field of biology, expanding our understanding of the principles that govern life and potentially redefining what we consider to be the essential conditions for its emergence. It would also underscore the incredible diversity of the universe and the myriad paths evolution could take under different circumstances. For now, the search for such life forms remains a captivating frontier at the intersection of biology, chemistry, and astronomy, driving us to keep an open mind about the possibilities that lie beyond our earthbound experiences. The entry of a rogue planet, defined as a planetary mass object that does not orbit a star and instead travels through space independently, into our solar system, would present a dramatic event with potentially profound implications, both scientifically and for the stability of our cosmic neighborhood. Initially, the scientific community would likely be electrified by the discovery. A rogue planet entering our solar system would offer an unprecedented opportunity to study an object that has evolved outside the influences typical of planets tied to a star. It could provide insights into planetary formation and evolution, the conditions of interstellar space, and the diversity of planetary objects beyond our solar system. Astronomers and planetary scientists would eagerly deploy a plethora of observation methods to study the rogue planet's composition, atmosphere, if any, surface features, and any accompanying moons or rings. However, the trajectory and gravitational influence of the rogue planet would be of immediate concern. If its path through the solar system brought it near any of the planets, the gravitational effects could be significant. The orbits of planets and other objects could be altered, potentially leading to increased asteroid and comet activity as they are jostled from their usual paths. In an extreme case, if the rogue planet came too close to Earth or another planet, it could lead to catastrophic gravitational disturbances, such as significant changes in orbit or even direct impact. The long-term gravitational effects could also pose problems. Depending on its mass and speed, a rogue planet passing through could disrupt the delicate orbital balance of the solar system, leading to more subtle but widespread changes over time. The stability of the asteroid belt, Kuiper belt, and Oort cloud could be compromised, increasing the likelihood of comets and asteroids being directed towards the inner solar system. Any potential threat from a close encounter would likely drive international collaboration in tracking and studying the rogue planet, assessing risks, and developing any possible contingency plans to protect Earth from impacts or other hazardous outcomes. In the broader perspective, the encounter with a rogue planet would serve as a stark reminder of the dynamic and unpredictable nature of the universe. It could potentially stimulate discussions about planetary defense and the importance of space surveillance and research to foresee and mitigate astronomical threats. While the scenario of a rogue planet entering our solar system remains hypothetical, it underscores the importance of vigilance and scientific inquiry in understanding and protecting our place in the cosmos. The confirmation of a signal from intelligent aliens would represent a watershed moment in human history, irrevocably altering our perception of our place in the universe. Humanity's reaction to such a discovery would likely span a wide spectrum of emotions and actions, shaped by individual beliefs, cultural backgrounds, and societal norms. Initial reactions could range from exhilaration and awe at the realization we're not alone in the universe, to fear and apprehension about the intentions of an extraterrestrial intelligence. Public interest in space and science would likely surge, driving increased support for space exploration and research initiatives aimed at understanding and communicating with the newfound intelligence. Governments and international organizations would play a critical role in coordinating a response, potentially leading to an unprecedented level of global cooperation. Efforts to decipher the message and formulate a reply would involve scientists, linguists, and experts across various fields, highlighting the importance of interdisciplinary collaboration in addressing challenges of cosmic proportions. However, the discovery could also provoke existential and philosophical questions, challenging long-held beliefs and assumptions about humanity, spirituality, and our place in the cosmic order. Religions and philosophies would be tasked with integrating this new understanding of our universe into their teachings and worldviews. The confirmation of extraterrestrial intelligence could raise concerns about the security and future of humanity. Debates would likely emerge around the advisability of responding to the signal and the potential risks of revealing our presence to a technologically advanced civilization. In the realm of culture and media, the confirmation of an alien signal would undoubtedly influence art, literature, and films, reflecting humanity's evolving relationship with the idea of extraterrestrial life. Social media and news outlets would buzz with speculation, opinions, and potentially misinformation, highlighting the need for responsible communication and education to help the public navigate the complexities of such a revelation. Humanity's reaction to a confirmed signal from intelligent aliens would be multifaceted, combining wonder, fear, curiosity, and the potential for profound unity or division. The event would stand as a pivotal point in human history, prompting us to reevaluate our understandings and beliefs about life, intelligence, and our pursuit of knowledge in the vast, mysterious expanse of the cosmos. Should Earth's orbit drastically change, a cascade of profound and life-altering consequences would unfold. Firstly, and most importantly, the climate would undergo tremendous shifts. An orbit closer to the Sun could usher in intense heat waves, capable of drying oceans and rendering parts of the planet uninhabitable, while an orbit further away could plunge the Earth into a deep freeze, challenging the survival of countless species. Seasons as we know them could cease to exist, disrupting ecosystems and agriculture upon which humanity heavily relies. Additionally, the altered gravitational pull between the Earth and the Moon could affect ocean tides, leading to unusual and extreme weather patterns. Beyond the environment, human health would be at risk due to increased exposure to solar radiation or profound vitamin D deficiencies in the case of reduced sunlight. In essence, a drastic change in Earth's orbit would jeopardize the delicate balance that allows life, as we know it, to thrive on our planet. The probability of a rogue black hole passing near our solar system is exceptionally low, but not entirely impossible. Space is vast and sparsely populated, making such an event extremely unlikely. Black holes, especially the supermassive ones lurking at the centers of galaxies, tend to stay put, anchored by the immense gravitational pull of the galaxy's mass. However, smaller black holes, the remnants of massive stars that have collapsed, could potentially move through space, albeit slowly. If such a wandering black hole were to approach the solar system, its gravitational influence could disrupt the orbits of planets, comets, and asteroids, potentially flinging them out of the solar system or sending them hurtling towards the Sun or Earth. The perturbation in the Oort cloud could increase the number of comets entering the inner solar system, posing a risk to Earth. The overall dynamics of the solar system could be altered. However, the sheer distances involved and the sparsity of objects in space make the scenario of a black hole passing near our solar system a fascinating but highly improbable possibility. Harnessing energy directly from a star, particularly our Sun, could revolutionize how humanity powers its civilization, marking a leap into a type of energy abundance only seen in science fiction. Imagine a scenario where we could tap into the Sun's power on a grand scale, far beyond our current capabilities with solar panels. The concept, often envisioned as a Dyson sphere, involves encircling a star with a vast array of energy collectors to capture a significant portion of its power output. This harvested energy could potentially satisfy all of our planet's energy demands many times over, leading to a near-limitless supply of clean energy. It would enable the end of reliance on fossil fuels, drastically reducing greenhouse gas emissions and helping combat climate change. Furthermore, such an abundance of energy could fuel unprecedented technological advancements, space exploration, and the ability to sustain growing populations while maintaining high standards of living. However, constructing such a megastructure presents colossal engineering challenges, requiring materials and technologies far beyond our current capabilities. Nonetheless, even striving towards such an ambitious goal could drive innovations in energy generation and space technology, pushing humanity closer to becoming a truly spacefaring civilization. Building a Dyson sphere, a hypothetical megastructure designed to encompass a star and capture its power output, presents a plethora of theoretical limits grounded in both our current technological capabilities and the laws of physics. First and foremost, the sheer scale of materials required is staggering. To encircle a star like the Sun, we would need resources far beyond what is available on Earth, necessitating the mining and utilization of materials from asteroids and other planets. The structural integrity of such a vast construct is another formidable challenge. The sphere would need to withstand intense heat and radiation from the star, along with gravitational forces that could tear weaker materials apart. Current engineering and materials science do not possess materials capable of withstanding such conditions over the vast areas involved. Energy distribution and management within the Dyson sphere would also present complex challenges. Transmitting the captured energy back to where it's needed, potentially across vast interstellar distances, would require innovations in energy storage and transfer technologies that are currently beyond our grasp. The gravitational effects of constructing such a massive structure around a star could have unpredictable effects on the local star system, potentially destabilizing the orbits of planets and other celestial bodies. Ultimately, while fascinating from a theoretical standpoint, the construction of a Dyson sphere is bounded by extreme engineering, material, and energy challenges, requiring leaps in technology and science that humanity has yet to achieve. A map of the entire observable universe would be a breathtaking mosaic of cosmic wonder, illustrating the vastness and diversity of the cosmos on an incomprehensible scale. This map would showcase an intricate web of galaxies, each a collection of billions of stars, spread across the expanse of space. Galaxies would be grouped into clusters, and these clusters into superclusters, forming a gigantic cosmic web with vast voids of seemingly empty space in between. At the largest scale, the observable universe would appear somewhat uniform thanks to the cosmic microwave background radiation, a faint glow left over from the Big Bang, visible in all directions and providing a snapshot of the universe when it was just 380,000 years old. This cosmological masterpiece would also highlight the filamentary structure of matter distribution, where galaxies and galaxy clusters align along invisible threads of dark matter. Interestingly, because of the finite speed of light, this map would also serve as a time machine of sorts. The further out we look, the older the light, allowing us to see back in time to the younger stages of the universe, approaching the Big Bang itself. However, it's crucial to note that this map would still only represent the observable part of the universe. Beyond this observable horizon, the universe continues, but it remains beyond our sight and current understanding, hinting at the unfathomable scale and mysteries still hidden in the cosmos. The notion that the laws of physics might differ in other parts of the universe is a profound and tantalizing possibility that challenges our understanding of the cosmos. Our current understanding of physics, encapsulated in theories such as quantum mechanics and general relativity, is based on observations and experiments conducted within our observable universe. These laws have shown remarkable consistency across vast distances and conditions, from the behavior of particles in colliders on Earth to the motion of galaxies billions of light-years away. However, some theoretical frameworks suggest that the physical constants and laws we observe might not be universal. For instance, in the concept of the multiverse, different universes within the larger multiverse could have fundamentally different physical laws, depending on how symmetry was broken in the early moments of their formation. Similarly, theories like string theory hint at the existence of extra dimensions that could alter physical laws at different scales or in different parts of the universe. Another intriguing possibility is that the laws of physics might gradually change over time or space, a concept known as cosmological natural selection, or the changing laws of physics. There could be subtle variations in physical constants or the strength of forces that would only become apparent over cosmological distances or timescales. Our ability to see deeper into space and further back in time is limited by several significant factors, stemming from the inherent challenges of astronomical observation and the current state of technology. One of the primary constraints is the finite speed of light. Since light travels at a constant speed, we can only see as far back as the light that has had time to reach us. This means the observable universe has a boundary beyond which the light has not yet had time to travel to Earth since the beginning of the universe. Another limiting factor is the expanding universe. As space itself expands, it stretches the light traveling through it, shifting it towards the red end of the spectrum in a process known as redshift. At extreme distances, this effect can shift light beyond the range of our current instruments, making it challenging to detect with existing technology. Technological limitations also play a significant role. Detecting faint light from distant galaxies requires highly sensitive instruments and techniques to filter out background noise from the Earth's atmosphere and within our galaxy. While instruments like the Hubble Space Telescope and the upcoming James Webb Space Telescope push the boundaries of what is possible, they still have limits in terms of resolution and sensitivity. Furthermore, the atmosphere of Earth itself obstructs our view of the cosmos. Atmospheric turbulence can blur images of celestial objects, while certain wavelengths of light are absorbed before they reach the surface. This is why many observatories are built at high altitudes, and why there is a growing reliance on space-based telescopes. Finally, our understanding of the universe is also limited by our theoretical models. As we look further back in time, we approach epochs like the cosmic dark ages and the Big Bang, where our current understanding of physics becomes less certain. Exploring these realms may require new theories or modifications to our existing models of the universe. Overcoming challenges in interstellar communication involves addressing the vast distances, ensuring signal clarity, and developing technology capable of facilitating such ambitious communication. Firstly, the immense distances between stars mean that even at the speed of light, messages take years, decades, or even centuries to travel from one star system to another. This delay makes real-time communication impractical and requires patience in waiting for responses to any signals sent into space. To ensure signal clarity over these vast distances, one strategy is to use highly focused and directed beams of radiation, such as lasers, for sending messages. This approach minimizes signal dispersion and increases the chances of the message being detectable over interstellar distances. Another method is to choose frequencies or types of radiation that are less likely to be absorbed, scattered, or otherwise disrupted by interstellar medium, cosmic dust, and celestial bodies. The choice of the radio spectrum, particularly the waterhole between 1420 MHz and 1666 MHz, is one such example, capitalizing on frequencies that are relatively quiet and can travel long distances through space with less interference. Technological advancements are crucial for both transmitting and receiving interstellar communications. This includes the development of highly sensitive receivers and large antennae capable of detecting faint signals from across the galaxy. Additionally, advancements in digital signal processing and error correction methods are essential for extracting and interpreting signals that have traveled such tremendous distances. Intelligent encoding of messages is also a significant challenge. Any communication intended for extraterrestrial intelligence needs to be encoded in a way that could be universally understood, regardless of the recipient's sensory modalities or cognitive structures. This might involve using mathematical and physical constants as a basis for creating a common language, as mathematics is considered a universal language that could be recognized by any civilization with a scientific understanding of the universe. These strategies, combined with international collaboration and sustained investment in research and development, form the basis of our efforts to overcome the myriad challenges associated with interstellar communication. As our understanding of the cosmos grows and our technology advances, so too will our capability to reach out across the stars, possibly making contact with other forms of intelligent life in the universe. In the boundless expanse of the universe, distant worlds hold the promise of elements and materials that defy our current understanding and stretch the imagination. While the periodic table guides our knowledge of elements on Earth and observed in astronomical objects, the unique conditions of distant planets and moons could give rise to unknown elements or exotic states of matter not found naturally on Earth. On planets with extreme pressures and temperatures, familiar elements might exist in forms that are alien to us. For example, carbon, under the intense pressure and heat of a planet much larger and hotter than Earth, could crystallize into forms of diamond vastly different from those known on Earth, or even form unfamiliar allotropes with properties we have yet to imagine. In the dense cores of neutron stars, matter is believed to exist in a state known as neutron-degenerate matter, where the atomic structure as we know it collapses under extreme gravitational pressure. This could give rise to neutronium, a hypothetical material composed almost entirely of neutrons, presenting characteristics far beyond the realm of traditional chemistry. The potential for entirely unknown elements also looms in the realm of theoretical physics, with some proposing the existence of islands of stability in the uncharted reaches of the periodic table. These are hypothesized regions where superheavy elements might exist with relatively long half-lives. unlike most synthetic elements created in laboratories that decay in fractions of a second. If such elements could be found or synthesized, they might exhibit novel chemical and physical properties, offering new technological possibilities. The hunt for unknown elements and exotic materials pushes the boundaries of exploration and science, driving us to develop new technologies and theories to probe the mysteries of distant worlds. As our capabilities grow, so too does our potential to discover the truly extraordinary, challenging our understanding of the natural world and expanding the horizons of human knowledge. Humanity's capacity to explore space is constrained by technological, physiological, and financial factors, but it is expanding rapidly with advancements in science and engineering. Currently, our direct exploration capabilities are limited to unmanned probes that have visited every planet in the solar system, rovers on Mars, and numerous orbiting telescopes peering further into the universe. Manned missions have reached the Moon, and plans for Mars are on the drawing board. However, the vastness of space presents daunting challenges. The nearest star system to us, Alpha Centauri, is over 4 light-years away. Reaching it with current propulsion technologies would take tens of thousands of years. Thus, interstellar travel, let alone exploration, requires significant advancements in propulsion methods. Concepts like nuclear pulse propulsion, antimatter engines, and even theoretical ideas such as warp drives and wormholes offer potential paths to drastically reduce travel times to other stars, but remain firmly in the realm of speculative science. The human body is not well suited to prolonged space travel. Issues such as muscle atrophy, bone density loss, and exposure to cosmic radiation present significant hurdles. Artificial gravity, advanced life support systems, and protective shielding are areas needing breakthroughs to enable long-duration manned missions. Financially, space exploration demands substantial investment. For broader exploration to be feasible, it requires not just funding, but also international cooperation to pool resources and share the rewards of discovery. Economic models like space tourism, asteroid mining, and in-situ resource utilization on the Moon and Mars could eventually underwrite more ambitious exploratory missions. As technology advances, humanity's footprint in space will expand. The scope of feasible exploration could grow exponentially if breakthrough propulsion technologies emerge, alongside advancements in life support and sustainable living in space. The potential is bound only by the limits of our imagination, resolve, and commitment to exploring the unknown. Our current space technology, despite its impressive achievements, faces several limitations that restrict our capacity to explore and utilize space more extensively. One of the primary limitations is propulsion. The chemical rockets we rely on for launching spacecraft are efficient for leaving Earth's atmosphere, but are less suited for long-duration interplanetary travel. They require large amounts of fuel, which increases the mass and cost of missions. Advanced propulsion methods, such as ion drives, nuclear thermal propulsion, and electric propulsion, offer higher efficiency, but are still in the early stages of development and application for deep space missions. Another significant limitation is the challenge of sustaining human life in space for extended periods. Space environments are hostile to human life, with issues such as exposure to cosmic and solar radiation, microgravity's effects on the body, including muscle atrophy and bone density loss, and the psychological challenges of isolation and confinement. Although we have developed life support systems for the International Space Station, these systems require continued resupply from Earth and are not entirely closed-loop, recycling all necessary life-supporting elements. Self-sustaining habitats that recycle water, air, and food are necessary for long-duration missions to Mars and beyond. Communication delay becomes a significant issue as we venture farther into the solar system. For instance, a signal from Mars can take up to 22 minutes to reach Earth, complicating real-time control of rovers and potentially impacting the management of crewed missions. Economic constraints also play a critical role. Space missions are expensive, requiring significant investment in research, development, and technology. While the commercial space industry is growing, reducing costs and increasing access to space, broadening our capabilities still demands substantial funding and international collaboration. Lastly, our current understanding of space and its environments limits our technology. For example, we are still learning about the long-term effects of space weather and the cosmic radiation environment on both technology and biology. As we venture into deep space, unexpected challenges could arise, necessitating adaptive technologies that are resilient to a wide range of space conditions. Despite these limitations, ongoing research and development in space science and technology continue to push the boundaries of what is possible. With advancements in propulsion, life support systems, materials, science, and robotics, among other areas, we will gradually overcome these limitations, paving the way for a new era of space exploration and utilization. The uncertainty principle, a fundamental concept in quantum mechanics introduced by Werner Heisenberg in the 1920s, states that it is impossible to simultaneously know both the exact position and exact momentum, velocity and mass of a particle with absolute precision. The more accurately we know one of these values, the less accurately we can know the other. This principle might seem at first glance to have little to do with the vast scales of space exploration, but it has profound implications for our understanding of the universe and the precision with which we can measure cosmic phenomena. In the realm of space and astrophysics, the uncertainty principle reminds us of the inherent limitations in our observations and measurements. For instance, when observing the light from distant stars or the cosmic microwave background radiation, scientists are essentially looking at particles of light, photons, and, by extension, observing the universe at a quantum scale. The principle implies that there are fundamental limits to the accuracy of these observations. This becomes particularly relevant when studying phenomena that straddle the line between classical and quantum physics, such as black holes or the behavior of particles in extreme gravitational fields. The uncertainty principle has significant implications for the detection of gravitational waves and the precise measurements required by experiments that use light or particles as probes of fundamental physics. Advanced experiments, like those using interferometers to detect gravitational waves, need to account for quantum uncertainties in their designs and data analysis to isolate the incredibly subtle signals they seek from a sea of noise. On a more theoretical front, the principle guides our understanding of the early universe, where quantum fluctuations during the period of cosmic inflation are thought to give rise to the large-scale structures seen in the universe today. These fluctuations, governed in part by the uncertainty principle, have left imprints on the cosmic microwave background radiation that astronomers study to learn about the universe's origins. While the uncertainty principle may pose limitations on our measurements and understanding, it also opens a door to a deeper understanding of the universe by highlighting the complex interaction between the quantum and cosmological realms. In facing these challenges, scientists are continually developing new techniques and technologies to refine our observations and push the boundaries of what is knowable, despite the inherent uncertainties dictated by the laws of physics. The long-term effects of exposure to cosmic radiation on humans are a significant concern for space exploration, especially for missions beyond Earth's protective magnetosphere, such as trips to Mars or extended stays on the Moon. Cosmic radiation consists of high-energy particles that originate from outside the solar system, including protons, helium nuclei, and heavy ions, as well as gamma rays and X-rays. Unlike on Earth, where the atmosphere and magnetic field shield us from most of these particles, astronauts in deep space are far more exposed. Long-term exposure to cosmic radiation may increase the risk of various health issues. One of the most significant concerns is an elevated risk of cancer. Cosmic rays can damage DNA, either directly by breaking the chemical bonds or indirectly by creating water radicals that in turn damage the DNA. This damage can lead to mutations, some of which may initiate cancer. Apart from cancer, cosmic radiation exposure can lead to degenerative tissue diseases, affecting the cardiovascular system and potentially leading to heart disease, cataracts, and circulatory problems due to damage to blood vessels and tissues. There is also concern about effects on the central nervous system. Experiments have suggested that high-energy particles might damage neurons, potentially leading to cognitive impairments, reduced motor function, and behavioral changes, impacting an astronaut's ability to perform tasks. Additionally, cosmic radiation could have detrimental effects on reproductive health potentially leading to fertility issues or impacts on offspring, although this area requires more research. To mitigate these risks, space missions incorporate several strategies. These include shielding on spacecraft and habitats, careful mission planning to minimize time spent in the most hazardous areas, and the development of medical technologies and protocols designed to monitor and counteract the effects of radiation. Research into more effective shielding materials, drugs that can protect against radiation-induced damage, and the use of magnetic fields to deflect cosmic rays are ongoing. Understanding and mitigating the long-term effects of cosmic radiation is crucial for the future of human space exploration, ensuring that astronauts can safely achieve and return from missions beyond our planet. Protecting astronauts from the dangers of deep space involves a multifaceted approach that addresses various hazards, including cosmic radiation, microgravity effects, isolation, and the risk of collision with space debris or micrometeoroids. To shield astronauts from cosmic radiation, spacecraft and habitats are designed with specialized materials that can absorb or deflect high-energy particles. These materials may include traditional shielding like aluminum, as well as newer, more efficient materials such as polyethylene or other hydrogen-rich substances that are effective at stopping charged particles. Researchers are also exploring the development of active shielding methods, such as generating magnetic fields around spacecraft to deflect cosmic rays, mimicking Earth's magnetosphere. Addressing the health effects of microgravity involves both preventive measures and in-mission strategies. Astronauts undergo rigorous physical training before their missions to build up muscle and bone strength. During missions, they use exercise equipment designed for space to maintain their physical condition, performing daily routines that counteract muscle atrophy and bone density loss. Additionally, advancements in spacecraft design aim to incorporate artificial gravity in the future, potentially through rotating habitats or modules that create centrifugal force. To tackle the psychological and cognitive challenges of prolonged isolation and confinement, careful selection, training, and support systems are in place for astronaut crews. This includes psychological screening during the selection process, training in conflict resolution and stress management, and providing means of communication with family and mission control. Real-time virtual reality environments and other technologies that can simulate familiar terrestrial environments are also being developed to help alleviate feelings of isolation. For the risks posed by space debris and micrometeoroids, spacecraft are equipped with multiple layers of protective shielding. Whipple shields, for example, consist of an outer layer that vaporizes upon impact, dispersing the energy of the collision, and subsequent layers that catch the dispersed particles, preventing them from penetrating the crewed sections of the spacecraft. The comprehensive approach to protecting astronauts in deep space reflects the complexity of the environment and the multitude of risks involved. Ongoing research and development efforts continue to refine and enhance these protection measures, ensuring the safety and well-being of astronauts as humanity reaches further into the cosmos. Mapping dark matter, the elusive substance that does not emit, absorb, or reflect light, but exerts gravitational effects on visible matter, presents several major obstacles. Primarily, the invisible nature of dark matter makes it inherently difficult to detect and map directly. Scientists infer its presence and distribution through its gravitational effects on visible matter, such as the motion of stars within galaxies or the bending of light from distant objects, a phenomenon known as gravitational lensing. However, these methods provide indirect measurements, complicating the creation of detailed maps. The vast scales involved pose a significant challenge. The universe is immensely large, and dark matter is thought to form a complex filamentary network known as the cosmic web, spanning across the cosmos. To map this structure, astronomers must survey enormous volumes of space, requiring extensive time and resources. Current and upcoming surveys, such as those conducted by the Euclid spacecraft or the Vera C. Rubin Observatory, aim to tackle this challenge by observing billions of galaxies over large portions of the sky. Yet the sheer scale of the universe means these surveys can only cover a fraction of the total volume. Distinguishing between the effects of dark matter and other phenomena can be challenging. For instance, modifications to the theory of gravity could, in theory, mimic the gravitational effects attributed to dark matter. Disentangling these possibilities requires precise measurements and a deep understanding of both dark matter and the laws of physics governing the universe. Theoretical uncertainties about the nature of dark matter itself complicate mapping efforts. While the cold dark matter model, which assumes dark matter consists of slow-moving particles, is the leading theory, alternative theories suggest different properties and distributions for dark matter. Without a definitive detection of dark matter particles or a complete understanding of their characteristics, assumptions must be made about its behavior and properties when trying to map its distribution. Despite these obstacles, advancements in telescope technology, data analysis techniques, and theoretical models are steadily improving our ability to map dark matter. Each new observation and study helps to refine our understanding of its distribution in the universe, bringing us closer to solving one of the most profound mysteries in cosmology. Preparing for unexpected discoveries in space exploration involves a combination of flexible mission planning, interdisciplinary collaboration, advanced technology development, and comprehensive training. Space is a frontier filled with unknowns, and while scientists can make educated guesses about what they might encounter, the history of space exploration has been marked by surprising discoveries. Flexible mission planning is crucial. Space missions are designed with objectives based on current knowledge, but incorporating adaptability into mission plans allows scientists to seize unexpected opportunities or address unforeseen challenges. This could involve reprogramming spacecraft to observe new phenomena or redirecting them to interesting targets discovered during the mission. Interdisciplinary collaboration broadens the scope of expertise and perspectives in mission teams, enhancing the ability to anticipate and respond to the unexpected. By involving scientists from various fields, such as geology, astrobiology, atmospheric science, and more, alongside engineers and mission planners, teams can quickly understand and leverage new findings. Advanced technology development plays a key role in preparing for the unknown. Instruments with greater sensitivity, resolution, and versatility enable the detection and analysis of unexpected phenomena. Autonomous systems and artificial intelligence can help spacecraft make real-time decisions when encountering unforeseen conditions, especially in environments where immediate human intervention isn't possible due to communication delays. Comprehensive training for astronauts and mission control personnel ensures that human teams can effectively manage unexpected situations. This includes simulations of various scenarios, from technical malfunctions to novel scientific discoveries, to develop problem-solving skills and decision-making capabilities under pressure. Fostering a culture that encourages curiosity and a willingness to adapt to new information is essential. Missions must balance their core objectives with the flexibility to explore the unexpected, as these serendipitous discoveries can lead to some of the most significant advancements in our understanding of the universe. As we end our journey through the mysteries of the universe, let us know your thoughts in the comments below. What do you think exists out there in the universe? Are we alone?